Hello everybody. Chapter 13, we're going to be getting into some probability stuff. As I told a couple of the classes, we're going to be going through this fairly quick. So some of this, and especially these first couple sections, is stuff that I'm sure you've done before. You probably remember it from way back in middle school, maybe even before. What we got here going on, I'm actually going to do 2 lessons here in one. It won't take long because this is going to, I think, be a real strongly oriented towards review for you here. I don't think there's anything that we're going to throw at you that's too terribly new. So 2 sections today. The first one being section 13.1 in the text. But what we're going to do is talk about experimental and then theoretical probability. You probably, again, have heard of that before. So what do you remember about probability? How is geometry going to make it new? All right, the vocab. I didn't really spell it out on my slides. So the outcome, an individual outcome, is the probability or the chance. The individual outcome is what is going to happen, okay? So we're rolling dice, for example. The outcome could be you roll a 1 or a 2 or a 3. Those are the possible outcomes. The event is what you're doing, rolling dice. The sample space. All right, the sample space is going to be all of the possible outcomes. All right, probability we will talk about. Experimental probability is spelled out. Theoretical we'll do. And then complement of event. Those definitions are coming later. All right, so let's get it going. All right, move that out of the way. So our key concept from the first part of the section. If the outcome in a sample space, if they're equally likely to occur, then the probability of an event, which we write this way, probability of an event with the little parentheses on them. Okay, so if the outcomes in the sample space are equally likely to occur, the probability of an event, we give it some numerical value between 0 and 1, and it measures the likelihood of the event. And the way we do it, we check the number of favorable outcomes, or what you want to happen. So say, for example, rolling dice again, you want the odds of what are the chances of rolling a 3? Well, the only favorable outcome then is 3 out of 6 possible outcomes. So for that example, our probability is 1. The chance of rolling a 3 out of 6 total. All right, 1 in 6, your chance of rolling a 3 if you have 1 dice. All right, so a 0 probability means the event is impossible. The probability of rolling a 7 on one dice, is 0. A 1 probability means that the event is certain to happen. So the probability of rolling either an even number or an odd is 6 out of 6 or 1. All right. Now we can also write probabilities as ratios or decimals or percents. Okay. But either way, we're looking at some sort of a scale ranging from 0 to 1. If we're talking percents, we're going to go 0 to 100%, right? Same kind of thing. Okay. 0 will never happen. 100 is certain to happen. Okay. Experimental probability. That means you're actually going to do the work. You are actually going to measure the outcomes over a certain number of times. Okay, so experimental probability of an event measures the likelihood that that event occurs based on the actual results of an experiment. So if you're actually rolling the dice, spinning a spinner, pulling marbles out of a bag, counting items, etc., and you tally the data, what you've got is experimental probability. Okay, so that probability is the number of times you count that actually the event actually occurs compared to the number of times you did the experiment. All right, I'll give you an example here a little bit later on experimental probability. Okay, here's one. Box of Crunch Berries has 6,000 pieces of cereal. All right, and some of them are Cap'n Crunch, and some of them are red berries, and some of them are blueberries. All right, so you choose 400 at random. You pull 400 samples out of the box, and you count 80 of them, and you find 80 of them are blueberries. All right. So the experimental probability, I'm sorry, I said that wrong. You count all 400, but you find that 80 of them are blue. Okay, so what's the experimental probability that one of these bits chosen at random would be a blueberry? Well, we take the number of blueberries out of our sample set, divide it by the total that we checked, and we find out that's 80 over 400 for a reduced fraction of 1 out of 5, which we can also count as 0.20 or 20%. Now, to answer the second question, that means we can get a pretty good estimate of the number of total blueberries in the box if we take that total, 6,000 pieces in the box, and we multiply it by the probability that we've got a blue one, and we come up with our 1,200. All right? Okay. Now, as opposed to experimental probability, theoretical probability is going to be based on calculations, okay? It describes the likelihood of an event based on mathematical reasoning. So, we don't actually roll the dice to know that the probability of getting a 3 is 1 out of 6, okay? So, without actually playing bingo, we know the probability of pulling, for example, I-17 is 1 out of 75 possible numbers that we could call, right? Without actually trying it out. Well, I'll let you read that one on your own. Theoretical probability based on mathematical reasoning. So, here's a spinner. We can't actually spin it. It doesn't actually work. But assuming that the probability of landing in any one of these 8 sections, 1, 2, 3, 4, 5, 6, 7, 8, assuming that probability is equal for each of the 8, what's the probability that we're going to land on green? Well, 3 of the 8 are green. Therefore, our theoretical probability would be 3 out of 8 is the probability of hitting the green. Now, we may do the actual experiment and find something different, which highlights the difference between theoretical probability and experimental probability, but our theoretical says that we're going to get 3 out of 8. Okay, the probability of getting a blue, I got one blue section there is all. Probability of getting a blue, 1 out of 8. All right, our probability of getting a blue or a green, well, we take the blue probability and the green probability, and we find out we got 4 spaces that are either blue or green for a probability of 4 out of 8, or 50%, or 1/2, however you like to think about it, okay? So, probability, theoretical. Now, the complement of an event, last vocab term, the complement of an event is all the possible outcomes in a sample space that are not part of the event, okay? So, if the probability of green is 3 out of 8, its complement would be, well, we got to consider the probability of what is not green, and that's going to be everything else. The reds and the yellow and the blue give us 5 out of 8, so the probability of green and the probability of not green, those are called complements. All right, notice that when we add complements together, we're always going to get 1. Okay, either it's going to happen or it's not. One of those things is certain, so the probability ends up being 100%. All right, section 13.2, we're just going to take this a little bit of a step farther and talk about how we use frequency tables, where we actually, this is referring to experimental probability, but we're actually going to use tables of data and then use that information to make predictions about what's going to happen or determine the probability of a certain event based on actual tables of data. All right, so I'm going to show you some frequency tables. We'll talk about relative frequency, and we'll talk about the probability distribution. Coming right up. All right, so a frequency table is a data display that shows how often a certain item appears in a category. So for example, we checked with 40 students to see what kind of music they liked. 10 of them said rock, 7 hip-hop, 8 countries, etc., etc. All right, so out of the total of 40, if we ask, for example, how many prefer rock, or what's the relative frequency of those who prefer rock, what we see is we got 10 who like rock out of 40 total. for a 10 out of 4 probability, or 1/4, or 25% of the students who like rock. All right. Since Yuma is country, well, the relative frequency of those who prefer country will be 8 out of 40 for a 1/5 or 20% probability that a student will like country music. All right. Now, of course, we can also use that to assume that, say, if we have 250 students in the school, how many of them like country? We take that 250 and we multiply it by our 20% or our 1/5, and we find the answer on that one. 250 times 0.2. I should know this one off the top of my head, but I'm not going to do it off the top of my head because I got my nice fun little calculator thing here. So 250 times our 20%, 50 students will like rock. Good. Or like country. I'm sorry. Good. Going from there. Say you toss a coin, 3 coins, and you do it 50 times, and you tabulate the results. The number of times you got 3 heads was 5, heads, heads, tails, 7, heads, tails, tails, etc., etc. All right, and we asked the question, what is the number of times you get exactly 2 heads? Well, I see 2 heads there. I got 2 heads there. And I got 2 heads there. So we're going to take 7 plus 6 plus 2 for a total of 15 out of the 50 times we did it. So the relative frequency of getting 2 heads, 15 out of 50, 3 out of 10, 30%. Good. Finally, a probability distribution. We would basically take all of the items in our sample set and figure out what the different probabilities are, each individual one, in this case 5 out of 50, 7 out of 50, 9 out of 50, etc., 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 and we would make a table that has all of the probabilities distributed for each of the categories, and we will notice that when we add them all up, of course, one of those 8 things has to happen, so the probability has to total up to 1. And that covers it, guys. So what I'm going to do for homework is basically give you just enough to keep you fresh on this. I think it's going to be fairly easy for you. But you got 2 parts to the assignment, page 827, page 833, and that'll be due Tuesday. So hope you liked it. Hope the probability is good, that everything goes well with this assignment, and we will see you all soon.